on page 107, we're given the limit. We're asked to find the limit as x approaches -4 from either side from the square root of x squared plus 9 minus 5 divided by x plus 4. I'm looking back, you may be right, maybe we did not do a rationalizing. We only looked at a piecewise defined function, simplification. That's true. Thank you. Very good. Okay, so every time we calculate a limit, we have to plug it in. I know it's a contradiction from what I said before, that x cannot equal -4. This is very clearly carved in stone. X approaches -4 from either side, but does not equal -4. But we do have to plug it in to see what type of limit we have to deal with. So what do you think is, where is the numerator going? Yes. Where is the denominator going? Right. So there is hope. It's possible that this limit exists. Okay, perfect. Definitely, which factor eventually I'm hoping to get rid of? X plus 4 indeed. That's the factor that creates the problem. But that's not clear for the numerator at all, right? I can't factor anything here. So there is something I need to do, which is need to multiply and divide. We normally never say, let's rationalize the numerator, but we have no choice. We have to rationalize the numerator in this case. So what do I rationalize it with? The reciprocal, very good. The conjugate, sorry. So the square root of x squared plus 9 plus 5, and the square root of x squared plus 9 plus 5. I should have copied the problem one more time because I don't want you to see the 0 over 0 over here and just get confused. So I'm gonna white it out because I changed the equal symbol into a product, so that doesn't have place in there. There's no place for that. Good. So then, can anyone give us the numerator? Do not drop the limit operator. Do not drop the limit operator till the very last step. Okay, so can anyone give us the numerator? I'm going to copy the denominator. Can anyone tell us how to write or what is left in the numerator? X squared plus 9 minus 25. Great job. Thank you. Perfect. So now we continue simplifying the numerator because there is nothing I can do to the denominator. So I have the square root, I'm sorry, I have x squared minus 16. How will I factor x squared minus 16? So this changes into x squared minus 16. It better be x plus 4. One of them. It's a must. And the other one, that's it. Is this okay? Any questions? X squared plus 9 minus 25 is x squared minus 16, and I wanted to save some time and paper, and I already factored it because I knew I was expecting an x plus 4. I have to. So it's x squared minus 16. That's why I wrote it here. So it's x plus 4 times x minus 4, correct?
My mind added x after that 9.
Oh, no. Good. Good, I stopped that. Good. So now I can determine the limit. The numerator goes to I dropped the limit operator, so I'm ready for the limit. Which one? Awesome. And the denominator goes to impossible. That would be a tragedy. So Negative 8 squared, or negative 4 squared is 16. 16 plus 9 is 25. The square root of 25 is 5, and 5 plus 5 is? That's it. So that's negative 4/5. So it's a good point to go back to. Once we rationalize, and the x squared plus the square root of x squared plus 9 minus 5 went to 0, the square root of x squared plus 9 plus 5 cannot go to 0. Is that clear? The negative one that goes to 0, but not with a negative in the middle, but not the one with the positive. Say it again.
I missed the change from the negative positive.
It's the conjugate. So this is 1. I multiply by 1 without changing anything. That's why the top and the bottom have to be the same. So when we multiply these two, we get negative 25. This a squared minus b squared. We did this on the first day of classes. A minus b times a plus b is a squared minus b squared. Simplified changes into x squared minus 16, and I need it factored. I mean, I can write the intermediate step here if you'd like. As x approaches negative 4 from x squared minus 16 divided by x plus 4, and that in parentheses, instead of writing it on the side. I don't want to confuse you in any way, shape, or form.
So we rationalize, we simplify, just so we can get back to the point of plugging that back in.
Because I removed the 0 over 0. By rationalizing, very good point, by rationalizing, I removed the 0 over 0. Because eventually I simplified the factor that was the culprit. No other factor creates 0 over 0 in this case, but x plus 4. So once I rationalized, the numerator became x squared minus 16. I was able to factor it. I found the common factor of x plus 4. It went away, and now I can drop the limit operator. Any questions? Is this okay? Good. So do we want to see other types? Any preference? What about 29? So the limit as t approaches 0. Any questions on the previous problem, please? Yes, please. Brian?
One little question. What does the negative 4/5 actually represent in this case?
Yes. Yes. So the function is given to us.
Right.
So here's the graph of the function. So we want to determine the value of the function as x gets closer and closer to negative 4 from either side.
Yeah. So it's just the limit.
Yes, and that is the limit.
Okay.
Yes, that's what it
I
means.
got confused because you dropped the limit operator. So
I drop the limit operator only when I apply the value one more time, and it's not 0 over 0. That's when it goes away. Very good question. So let's go back for a second. Thank you. So when I make in this expression now, when I replace x by negative 4, I'm done. The limit operator gets dropped. I cannot write that this is limit as, again, as x approaches negative 4 from negative 8 over 10. I could, because we know from last time the limit of a constant is the constant, but there is no need. Once I replace x by negative 4 and I do not get 0 over 0, I can continue. I can drop the limit operator and I determine the limit. So when x approaches negative 4, this approaches negative 8, this approaches 10, and it's done. You can, if you want, to put the limit operator one more time, but do you know that the limit of a constant is the constant itself? Better? Okay, thank you. Good, so we're looking at 29. So this is 1 over t, the square root of 1 plus t, minus 1 over t. Okay, what do I do with this?
Similar basis.
So I would like to do this, limit of this minus limit of that. We just discussed the limit laws. And the limit law, the difference of the two, it says limit of this minus limit of that. Is it a yes? Is it a go or not? Very good. But can I separate? Excellent. But can I separate, say limit of this minus limit of that?
Yes.
The answer is no. And why?
Because 1 divided by 0.
Because the limit of this does not exist and limit of this does not exist. If the limits are not numbers, we cannot separate. So be careful. That's the first assumption of the limit laws. The limit laws are not applicable if the limit of both function is not a number.
So the first thing we always do is check to see if
We always check.
applies.
Yes. Yes. And then we go ahead. Of course, if the assumptions are not there, they're not fulfilled, I can't use the limit law. So yes, as you said perfectly, we have to find the least common denominator. Can anyone give us the least common denominator of these two fractions?
T times.
Very good. So what do you multiply the top of the first fraction by and the top of the second fraction by? The first one doesn't need anything, or you just write 1 or nothing. Well, what does the second one need? Is that okay? Good. So the numerator is 1 minus the square root of 1 plus t. Now I'm going to plug it in. I hope it's 0 over 0. I really hope it's 2/3, so I don't have to do anything. But if it's not 2/3 or 1/5 or whatever else, then I hope it's 0 over 0. What is it when I plug it in? 0 over 0. I agree. Good. So now let's look at the problem and decide what to do. What is the problem here? What is the culprit that eventually I hope to get rid of? 0. The culprit is 0. A factor of t from the top and a factor of t from the denominator should go away eventually, hopefully. There is nothing I can do here because this is not the problem. This approaches what? This quantity, just this quantity. I'm not going to drop it, but this quantity approaches. Okay, so that's not a problem. This is the problem. There is nothing I can do about it. So let's go back here. What do I do with this?
Multiply by 5.
Yes. Exactly. Because I'm lazy, I'm just going to write the denominator because it's easy. And I'm going to wait for you to give me the numerator. So it's 1 minus,
1 plus 2.
in parentheses. Very important. If we don't put in parentheses, we will not distribute. Or we distribute from the very beginning and not put parentheses, but we have to distribute -1 to both. Is this okay so far? Is that a yes? Is that a no? Any questions? Is it okay?
So you decide which the numerator and denominator. You decide which one to get rid of.
This is the problem that gives 0, not this.
Okay.
I will never rationalize this because, first of all, if I rationalize, it's the same thing. It's not going to go away. So this is the problem. This is what gives 0. This I cannot touch because what can I do to t? Nothing. This I cannot touch is not even a problem. This approaches 1. So the problem is this. That's the only thing I can work on. So I will multiply and divide by the conjugate. Is that okay so far? Is the next step clear? A minus b times a plus b. First day of classes. A squared minus b squared. Is that clear? Should I write that down or? So this is a minus b, and this is a plus b. So this is a squared minus b squared. Yes? Okay, so then we have limit as t approaches 0. The numerator is 1 minus t, and the denominator is this. What happens next? One with -1 is 0. I'm going to write it one more time for you to see what's happening here. Negative t, t, the square root of 1 plus t, 1 plus the square root of 1 plus t. Is the problem going away or not? The problem is going away happily. That was the problem. We expected to remove a t from the top and a t from the denominator. Now everything is done, nice and clean. Where does the numerator go? Where does the denominator go? Let's take it piece by piece. Where does this go? Which is? Good. Where does this go? Where does this go? Very good. Any questions? Okay, do you think we need more examples?
So again, for these scenarios, it sounds like rationalize, simplify, and then plug it in. But we're getting rid of anything that whatever causes the numerator or the denominator to be 0.
I'm more interested in the denominator. Because the numerator is 0, it's okay. But the denominator, if it's 0, it's not okay. Yeah. Anything else? So we looked at these. Now, of course, we don't have time for all of them, but I'll be more than happy to work on any other problem. And if you'd like to work on any absolute value, we can choose another absolute value. Is that a yes? Uh, 44? Okay, let's do 44 and then continue with a theorem that we need to discuss here.
Is this also on page 107?
Yes, 107, yes, 44. And the limit is limit as x approaches negative 2, 2 minus the absolute value of x divided by 2 plus x. The problem, a similar problem like this, where you will see again, and it will ask you first to simplify the function. Disregard this, I don't care what this means. I need to fully simplify the function first. So before I look at the limit. Okay, perfect. So where is my starting point? Where do I start? So one more time, the function is 2 minus the absolute value of x over 2 plus x. Where do I start? With what? With what? With the absolute value, of course. This is the only piece of this function that has two options, and that's where I have to start. Is that clear? Okay, so what are the options for the absolute value of x?
Minus x.
X when x is greater or equal to 0, or negative x when x is less than 0. Now we put the function together, 2 minus the absolute value of x over 2 plus x. When this is x, for x greater than or equal to 0, that's all I can do. There is nothing for x greater than or equal to 0. There's nothing else. Now, here's the second option. With minus negative x, what do I have at the top? 2 minus negative x will be? Excellent. Over 2 plus x, which is? Perfect. 1 for x less than 0, but not what? Excellent. Not negative 2. Exactly. Not negative 2. Very good. Any questions so far? Now I'm ready to determine the limit. I simplify the function fully. This is the simplified form of the function. No one can simplify it any further. So now I want limit as x approaches -2 from which branch? Which branch? I have to choose either this or this. I cannot choose both. Yes. So then the answer is?
1.
That's it. Very good. Very good. Questions? Questions?
Your parentheses around the blank.
It's parentheses around the function. I didn't really want to write it like this, but it's fine. It doesn't matter. So the parentheses are in the way. They get in the way or something.
Mentally trying to figure out what that. It's not like f of x anymore. What am I looking at? Just a number?
That's what you have.
It is f of x.
It is.
It is f of x. Okay.
Yeah, it is f of x, but it's this. Because -2 is in this interval, and it doesn't matter that the function is not defined at -2. The limit still exists, as long as the left and the right limits are the same.
So you picked one because -2 is right. That makes sense.
How do we know this?
Could you plug it in?
Both sides.
But let's plug in from the left of -2. What do we get? Let's plug in from the right of -2. What do we get? There's nothing else. It's just a number. Is that okay? Good. We can work on other limits in a minute, but I'd like to talk about one theorem, and I want to show you a picture because I like the picture. I will reproduce the same picture, and I will in a moment, but I just like this, the way it looks. And it's in colors. I have colors too. So here is a limit. You can say, where is the limit? I'm telling you, I'm interested in determining the limit of a red function. And I don't have any particular algebraic way or method to determine the limit of the red function. But I can say, and I can look at, when we look at this function and we realize that there is an upper bound somewhere near 0. I don't care what happens here. The function can do this here and cross up and down. I don't care. But around 0, on a closed, on a small interval, in the vicinity of 0, open interval, I see that the red function, we say, is squeezed or sandwiched between an upper function and a lower function. Would you agree with what we see, right? So it's squeezed or sandwiched between around the near 0, in the vicinity of 0. That's number one. If I show you that the limit of x squared when x approaches 0 from either side is 10, of course it's not. And if I show that the limit from the lower function as x approaches 0 from either side is 10, as an example, I determine the limit from the red function. It's sandwiched between these two near 0. If the limit of this and the limit of that both exist and they're 10, what could the limit of the red function be? Absolutely. So this is called the squeeze theorem. Some call it the sandwich theorem. Okay, so the squeeze theorem. And you'll see it in applications in a minute. So here's the idea. I'm simply going to copy that graph. So here's one graph of the upper function, let's say x squared, or any function. I don't care for, so let's say the upper function is g of x. The lower function is h of x. And the function we are really interested in is this function, f of x. The first hypothesis of the theorem is that f of x is squeezed between h of x and g of x near 0, or near a. If this is just the number a, it doesn't matter, near a. The second hypothesis is that the limit of h of x and the limit of g of x, when x approaches a, of course, in both cases, is the same number. Both limits exist and they equal 10. So by Squeeze theorem, the limit of, by the Squeeze theorem, then the limit as x approaches a from f of x must be guaranteed to be what?
No.
That's it. It makes sense. So the function is right here, squeezed between my hands. If the limit from the top is 5 and the limit from the bottom is 5, after I show that it's squeezed around that point, the limit from the function must be 5.
You moved on that top sheet just so
Yes, of course. Sorry about that. Okay, so here's an example that I'm hoping will convince you of the value of the theorem when the function is not even given. So I like to start with 38 on 107. We're told that 2x is less than or equal to g of x is less than or equal to x to the 4th minus x squared plus 2 for all x, all the time. For all x, in other words. Find the limit of g of x when x approaches 1. I don't even have the function. How can I determine the limit if I don't even have the function? We know that when we calculate limits, we have to plug in 1 in this case. What do I plug it in? I don't have the function. But this is already the first hypothesis of the Squeeze theorem. They're already giving us the lower bound, I'm going to call it h of x, and the upper bound function. In this case, since they denoted this by g, I'm going to denote this by f. So the first hypothesis is already given to us. They're telling us for all x, g is squeezed between lower bound, lower function h, upper function f. Now what do I have to do as the second step? Find the limit. So then find the limit as x approaches exactly of 2x, and the limit as x approaches 1 from x to the 4th minus x squared plus 2. Before we calculate those, if both limits exist and if both limits equal blah, then what do we conclude about the limit of g? Equals blah, of course. Good. So then what is the limit of the first? Good. What is the limit of the second? Good. So then from 1 and 2, by the Squeeze theorem, the limit of g of x as x approaches 1 must be, that's it. So that's one type of application, one application of the Squeeze theorem, when we don't even have the function, and we can still determine a limit. The second type of application requires a little bit more work. So let's take a look. Ready for this? Any questions on this? Pretty straightforward? Okay, perfect. Okay, let's look at 39. Same page. Limit as x approaches 0 from either side of x to the fourth times cosine 2 over x. We're asked to determine this limit. And of course I have to plug it in and see what this is happening, what's happening here. Where does this go? Good. Where does this go? Correct, Brian, thank you. So remember the graph. Please do not forget this graph. Please, it will make your life easier. This is a graph of 1 over x. 2 over x is the same, doesn't matter. So as x approaches 0 from either side, where does 1 over x or 2 over x or 10 over x go? It doesn't matter. It goes to, on one side to infinity, on the other side of 0 to negative infinity. So what is 2 over x? Where is 2 over x going? 2, I have no idea. And now I'm asking you, what is cosine of I have no idea? Exactly. Excellent answer. That's the correct answer. So my only escape is the squeeze theorem. My only chance. So let's think. Where do I start? Well, I start with cosine. Why do I start with cosine? Is because I know that cosine is a bounded function. What is the upper bound of cosine forever for anything? And what is the lower bound of cosine forever for anything? So the upper bound is 1 and the lower bound is -1. Awesome. So what did I do so far? I built something for this piece, but that's not my function. This is the function. So I'm thinking of doing what to all 3 sides? Multiply by x to the fourth, all 3 sides. However, we have to pay attention to one very important item. I have to make sure that x to the fourth is not 0, because I'm not allowed to multiply by 0, 3 sides of the compounding inequality. And I have to make sure that it's positive, because if it is positive, then I don't have to switch the inequality symbols, right? Right? But if it's negative, then I have to switch the inequality symbols. So I have to be careful. I don't have any problem. Why? X to the fourth is always positive, no matter what. And it's never 0 because the limit says x approaches 0. It's not 0. So we will multiply all 3 sides by x to the fourth. Negative x to the fourth less than or equal to x to the fourth. Cosine 2 over x less than or equal to x to the fourth. Is this okay so far? Are you okay? You're not feeling well? So sorry. I hope to see you on Monday. Is this okay?
So you got -1 and 1
From trig.
Yep.
Yeah, the maximum is 1, the minimum is -1. So we multiplied all 3 sides by x to the fourth. Because it's not 0 and it's positive. We don't have to switch inequality symbols or anything. So this is greater than 0. So now I have indeed in the middle the squeezed function. So this is the first hypothesis. This is the lower bound. It doesn't matter how you want to call it. Let's call it h of x. And this is the upper bound. Let's call it g of x. So I showed that the function that we are trying to find the limit from is squeezed between 2 functions. An upper one, which is x to the fourth, and a lower one, which is negative x to the fourth. Number 2. What do I have to show in number 2 in order to determine this limit? Or what am I calculating? What am I after now? Very good. The limit of negative x to the fourth when x approaches 0 from either side. And the limit of x to the fourth when x approaches 0 from either side. If these happen to exist and be the same, then I solved the problem. I found the limit. by no other method, no factoring, no rationalizing, no nothing, just the squeeze theorem. No other method works here. So then, what is this limit? What is this limit? So therefore, this is 0, but I have to write y. So I will write from 1 and 2 by the squeeze theorem. So from 1 and 2 by the squeeze theorem, limit of x to the fourth cosine 2 over x as x approaches 0 from either side is then definitely 0.
You said by 1 and 2
By 1,
those two steps.
the first hypothesis,
Yeah.
and by 2, the second hypothesis being fulfilled. Both conditions or hypotheses of the squeeze theorem are fulfilled. Therefore, from number 1 and 2 together, I conclude that the answer is 0 by the squeeze theorem.
So this answer is incorrect without the verbiage in the beginning, without writing from 1 and 2.
Yes, you have to show 1 and 2. Yes.
Okay.
Yes. Thank you. Very good question. Thank you. Perfect. Any questions? Anything else? Anything else? Okay, 2.4. We're not finished with limits, with different limits. So we still continue to look at those. Sean, can I borrow your handout just for 1 second? What I would like you to work on for Monday, from the handout, you can do number 1, you can do number 2, we did it in class. You can do number 3, you can do number 6, we just did number 9. Please do it again just for you to make sure that everything is clear. You can do number 10. Now we just did this together. You can do number 11. It's just this a minute ago. You can also do number 12. The rest not yet, because we did not get to those yet. Thank you. Okay, so from the handout, 1, 2, 3, 6, 9, 10, 11, 12. And please ask questions on Monday if you think that anything needs addressing. Okay, 2.4 is the only formal proof that we will see in this class. You will see in other classes, but not in this one. Just this is the only formal proof. We use two different verbiage, if you want, for the same thing. One is the one I like because it's shorter. Epsilon delta definition of the limit. Epsilon delta definition of the limit. The precise definition of the limit. I prefer epsilon delta, but you can say it's the same thing, the precise definition of the limit. I'm going to show you the mechanism and what happens here, and then we are going to write the epsilon delta definition or the precise definition of the limit. So let's take a look by comparison, two different graphs. Bless you. I'm going to use numbers for simplicity, but then when we write the definition, we are not going to use numbers. I will repeat myself several times on this till you understand it and can follow. Don't get upset from the very beginning. You will understand it. And we'll choose a couple of examples and I'll let you work on one. Okay. Don't look at the second one just yet. Let's look at the first one. And here's my claim. The limit of f of x as x approaches 5 is 7. Now, I would like you to tell me whether you agree with this or you don't. You have to agree because that's what it is. Good. Thank you. So, assuming now that I zoomed in and I chose an interval that is symmetric interval around 7, as small as you wanted it to be. It could be 8 and 6, but it could be 7.01 and here 6.99. Correct. As big as you want it to make, or as small as you want it to make, because that's the idea, right? And I will always be able to find this interval. I select the width of this interval, and that is epsilon. So obviously the upper point will be 7 plus epsilon. Epsilon can be 0.1, 0.01, can be anything you want. And obviously the bottom part of the symmetric interval will definitely be 7 minus epsilon. So I can create around 7 an interval of the width that I select. And the following will always happen. What will happen? For every epsilon, I draw horizontal lines. These horizontal lines meet the graph in respectively 2 different points. So for every epsilon, I will find this point, and I will find this point. And from there, I come down to x. And I will always be able to find a corresponding, what do you think? Of course, thank you. A corresponding delta. But it has to be, I have 2 options. This is one option with the smallest of the 2. And I have this option with the bigger of the 2, right? So I have this epsilon, or I have the blue epsilon. If I choose the blue epsilon, then when I choose an x here, f of x for that particular value will fall definitely within epsilon, smaller distance than epsilon, away from the limit. If I make the mistake to choose the largest of the 2, here's what happens. I may select x here, and then will f of that particular x fall within epsilon away from the limit? No. So I will always have to stick with the smallest of the 2, not the larger of the 2, because one on this side is larger and the this side is smaller. I will always choose the smallest of the 2. Why is this mechanism possible for every epsilon? Because the limit exists. So now imagine that you zoom in further, you find a smaller epsilon, you will find the corresponding delta, you will choose the smallest of the 2, so that if you pick x here, f of that x will fall within epsilon away from 7. You choose another epsilon, as small as you wanted it to be. You will always find the corresponding delta near 5, around 5, such that when you pick x here inside this interval, f of x is guaranteed to fall within epsilon away from 7. Why is that true? Because the limit exists. So the key word here is for every epsilon. For every epsilon. Now, let's go to this example. I claim that the limit exists. That's my claim. And yes, you're going to say you lost your mind. And I'll say, well, let me show you. It works. I can choose this interval. And from this point here, I will be able to find a delta. This appears to be bigger, so I'm going to find this delta. Such that when I pick x, it will fall within epsilon away from 7. So the limit exists. And you can say, not so fast. You are forgetting something very important. You are forgetting this word, or maybe these two words. For every. I'll show you one that it doesn't work. Look, if I want this epsilon, I'm in trouble. I cannot find an interval around 5. I'm stuck. But for this epsilon, or for this epsilon, or for this epsilon, or for this epsilon, I can. I may be able to show you for a billion epsilons that the limit exists, but not for every. So the limit does not exist, because I cannot show you the mechanism for every epsilon on the planet. I can only show you for a billion of those, but the limit does not exist. On that side, I can show you that mechanism works for every epsilon. And no matter how small you want it to be, you will always find a delta, so that when you pick x here, f of x will have a distance smaller than epsilon from the limit. If you say that we understood the mechanism, then I'll present the definition. First in plain English and then with symbols. Do we understand the mechanism? Okay, one more time. Because I'm going to put this in writing now. For every epsilon positive, I will find delta positive, such that when I pick x with a distance between x and 5 smaller than delta, not here. When I pick x with a distance from x and 5 smaller than delta, f of x will fall here, meaning the distance between the function n7, the function value n7, will be smaller than epsilon. Guaranteed. Should I say it again? Okay. So for every epsilon, I will determine a corresponding delta for every epsilon near 7, right? Around 7. I will find a corresponding delta around 5. This was my 5. So that when I pick x here with distance between 5 and x smaller than epsilon, smaller than delta, f of x will find itself between 7 and 7 plus epsilon, or maybe here between 7 and 7 minus epsilon, so that the distance between f of x and 7 will be less than epsilon.
So delta is defined as like the bounds of delta given just the corresponding x for, in this instance, 7 plus some epsilon, the same bounds.
So it will, yes, it will. So for every x that you pick here, the distance between 7 and that f of x would be less than epsilon, only because the limit exists. Otherwise, this mechanism will not work. Okay, how do we write this and put this in writing? So first in plain English. And now I'm going to use L for this and A for that, because it works for anything. So limit as x approaches a, in general, from f of x is L. And this is the double equivalency symbol, meaning from left I can get the right, from right I can go back to the left. And now again in plain English, for every epsilon positive, I will find, and this is important, a corresponding, it will depend on epsilon, delta positive. So one more time, for every epsilon positive, I will find the corresponding delta positive such that when I pick x with distance from A smaller than what?
Smaller than delta.
Of course, thank you very much. F of x, the function of that x, will definitely that function value will definitely be at a distance from L that is definitely, again, if you do not have to, is smaller than. Thanks. That's it. So for every epsilon positive, I will find a delta positive such that when I pick x with a distance smaller than delta from away from A, its corresponding f of x will be at a distance from L smaller than epsilon. We're not going to write this. We're going to write something which I hope you're going to find much easier. But I have to show you three mathematical symbols. This mathematical symbol stands for every or for any. This mathematical symbol stands for there exists. And this mathematical symbol was such as. Also, how do I write the distance between x and A?
Delta symbol is triangle.
And how do I write the distance between f of x and L? Is there anything in mathematical, from your mathematical background, that triggers the idea of distance? Is there any?
Distance one.
Say it again.
Distance one.
True, but some symbol that represents the distance.
It's the minus one. Absolute value.
That's the one that says distance, right? So then the distance between x and A is this. How do I write the distance between f of x and L? That's it. So please remember these. That's the distance. The absolute value of x is the distance between x and 0. So now we're going to use all these symbols, 1, 2, 3, 4, 5, and write this in only one row, not 6. Ready?
I'm still confused on why would you select absolute value? Will it make sense once you write it out or something?
That's the distance. The distance between x and A is the absolute value of x minus A.
Because you can't do that.
It doesn't exactly. It can be so. This is A, and you pick here, or you pick here.
Okay, all right. Now I get it. All right.
So that's the distance. Very good. Good question. So we have to start. That's the starting point. The limit of f of x as x approaches A from either side is L. The double equivalency symbol. And here is, you're not forced to use these symbols. You can use plain English, but you have to write it somehow. Okay, so because I don't think I have enough room here, so I'm going to continue here. For every epsilon greater than 0, there exists a delta greater than 0, such that 0 less than x minus a less than delta implies f of x minus L less than epsilon. Let's discuss every piece one more time. It's still just one row. I write big. Okay. So for every epsilon positive, I will find a corresponding delta positive such that the distance between x and a, when I pick x close to a, the distance less than delta. Why do I need this? What is this 0 less than that? I know that the absolute value is positive. Why do I need that in there? To avoid what?
Could you say the question?
Yes. So why do I, this is redundant, isn't it? I know that the absolute value is greater than 0. Why do I have 0 less than, to avoid what? Exactly, to avoid equal x equals a. I cannot pick a. Exactly, that's the reason why. As you see, because it does not have the equal symbol, this means you cannot choose x to be a. And we know that. X approaches a. I cannot choose x to be a. X approaches a. So this cannot be 0. And this is exactly what it's signifying. Make sure you don't replace x by a. You can't do that. Okay? So for every epsilon, I will find the corresponding delta. It will depend on epsilon, such that every time I pick close to a, but not a, less than delta, the distance is less than delta, the distance between f of x and L will guarantee to be less than epsilon. We are only going to, allow me to stop